Hey everybody, welcome back. This is section 12.13 on the isomerization of cycloalkanes. So our goals in this section are to be familiar with the concept of cycloalkane constitutional isomers and to be able to distinguish cis and trans isomers of cycloalkanes. So constitutional isomers, structural isomers, are possible for cycloalkanes that contain 4 or more carbon atoms. So anything that has 4 or more carbon atoms can make isomers. So for example, cyclopentane, isomers of cyclopentane include methyl cyclobutane. It's 4 rings, 4 carbons in the ring, so that's cyclobutane, and then with a methyl group sticking off. 1,1-dimethyl cyclopropane, 3 carbons in the ring, so that's where the cyclopropane comes from. And then 1,1-dimethyl is showing these 2 methyl groups. 1,2-dimethyl cyclopropane, we still have 3 carbons in the ring, 2 methyl groups located at positions 1 and 2. And then ethyl cyclopropane, we have 3 carbons in a ring, and then we have an ethyl group, and it's the only substituent group, so we don't have to include a number. These all contain 5 carbons, C5, and 10 hydrogens. So any cycloalkane that has 4 or more carbons can make isomers. We can have isomers of that cycloalkane. So in addition to constitutional or structural isomers of cycloalkanes, isomers that have different connectivity, you can tell they have different connectivity, of course, by drawing them, but also when you name them, even though all of them are C5H10, when you name them, they each get a different name. And that's another way to tell that they're an isomer. If they end up with a different name, then they're going to be an isomer. Different name, but the same molecular formula. There's also what are called stereoisomers for cycloalkanes. And a stereoisomer is an isomer that has atoms in the same order. So the atoms are connected in the same order, but they're arranged differently just in 3-dimensional space. So compounds that are cis-trans isomers, a type of stereoisomer, oftentimes when we draw them on paper in 2-dimensional space, they may look identical. And you think, oh, these aren't isomers. But in 3-dimensional space, the atoms are arranged in a different arrangement. So cis-trans isomers are going to have the same molecular and structural formulas, but they're going to have different orientations of atoms in 3-dimensional space due to restricted rotation around the single carbon-carbon bonds in the ring. So restricted rotation about rings occurs in single bonds that are part of a ring structure or double or triple bonds. So we previously talked about conformers, right? That you could have rotation about a single carbon bond, and you could have momentary or temporary isomers, which we call conformers or conformations. But cis-trans isomers for cycloalkanes, because even though we have single carbon-carbon bonds, the carbon-carbon bonds can't rotate because they're locked into place from the ring structure, versus a carbon-carbon single bond here that can rotate. It's not locked into place. So carbon-carbon single bonds that are not part of a ring structure, there's free rotation, you get conformers. But if the carbon-carbon single bond is locked in a ring structure, or it's a double or a triple bond, then you don't get that bond rotation. This is when you can get cis-trans isomers, when the carbon-carbon single bonds can't rotate, or if you have a double or a triple bond. So cis means the same. So a cis isomer means that 2 similar structures or groups are on the same side of a carbon-carbon bond that can't rotate. So the carbon-carbon bonds that don't have free rotation are single bonds that are in a ring, double bonds, and triple bonds. So if you have a cis isomer, what that means is that 2 similar groups are on the same side of the bond. Like these are both up above this bond that can't rotate. So cis in chemistry means same side. So in this case, these two CH3 groups are on the same side. They're both up from the bond that doesn't have any rotation available to it. A trans isomer is where the two groups across a bond that can't rotate. So here's our carbon to carbon bond. It has no rotation because it's locked into place from this ring structure. And our two CH3 methyl groups are on opposite sides of the bond. So trans in chemistry means on opposite sides or across from. So in this case, our two CH3 groups are across the bond. One is up and one is down. So we would call this a trans isomer. These two structures have the same molecular formula. They have the same connectivity, right? There's a 5-membered ring, and then at carbons 1 and 2, there's methyl groups. A 5-membered ring, and at carbons 1 and 2, there's methyl groups. So they'd have the same names, but we'd add in italics at the front of the name, whether it's the cis or the trans orientation of these groups next to the bond that can't rotate. So cis means the groups are on the same side, they're close to each other, and trans means they're on opposite sides of the bond that doesn't have free rotation. So we can add this to our flowchart of isomers now. So we talked about that isomers are molecules with the same molecular formula, but they have different arrangements. And the first type of isomer you always learn about are what are called constitutional or structural isomers. These are isomers where the connectivity between the atoms is different. They're bonded in a different order. And these are called constitutional or structural isomers. These are the ones right here. And so you go to your flowchart, do the compounds have the same molecular formula? If they don't, they're not going to be isomers, game over. If they have the same molecular formula, if they have the same connectivity, they're going to be a type of stereoisomer. And if they don't have the same connectivity, their bonding pattern is different, they're going to be a constitutional isomer. So that's kind of the first one we always learn about. And then if they have the same connectivity, if they can be interconverted by rotation about single bonds, they're what we call conformational isomers. These are the ones where there's a carbon-carbon single bond. And even if there's two different groups, like here we have a methyl group and a methyl group, because there's free rotation about this single carbon bond, temporarily the two methyl groups might be opposite each other, and then the bond rotates, and the two methyl groups are next to each other again. So these are called conformational isomers or conformers, and they just exist momentarily. So we don't really consider these as like separate compounds because they're just a temporary existence. That bond is always rotating, so we can't really like lock them into place necessarily. So if the compound can't be interconverted by rotation, if your answer is no, that's when you get into configurational isomers. And if the isomerism is at a double bond or a ring, this is what we're dealing with here, geometric isomers. So we have trans, which means the two groups are on opposite sides of the double bond or the single bond in the ring that can't rotate, and cis, which means they're on the same side. So geometric isomers are a different arrangement of atoms in three-dimensional space next to a double bond, a triple bond, or a single bond that's part of a ring structure. Any bond essentially where you don't get free rotation about that bond. And for carbon atoms, that's going to be, again, single bonds that are part of a ring, double bonds, or triple bonds. And then, of course, there's more types of isomers. They can get really complex. And we're not going to go into diastereomers and enantiomers in this class. Okay, that is it for section 1213 on isomers of cycloalkanes. Ones to keep in mind are that cycloalkanes, if they have 4 or more carbons, they can make constitutional or structural isomers where the actual arrangement of the atoms is different. And cycloalkanes, if there's substituent groups sticking off of the cycloalkane, they can make cis-trans isomers with those substituent groups if they're next to each other. If the two substituent groups in three-dimensional space are on the same side of the non-rotational bond, they're called a cis isomer. And if the two substituent groups are on opposite sides of the non-rotational bond, it's called a trans isomer. Okay, that's it for this section. We'll see you next time. Thanks.